بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. يسرني أن أقدم هذه المداخلة بعنوان AI in Telecommunication or in Telecom Industry. I am Ustad Ahmed Roman from the National Telecommunication School, University Oran. So the evolution of telecommunication can be visualized in this diagram, where we're focusing about generation from 2G to 5G. And in these recent years, we are talking about the 6G. So the evolution from this generation is very significant in terms of data rates and latency, and also what we call massive machine type communication, or enhancing the density or the capacity of the network to receive a lot of user or a lot of connectivity. But the question that we want to ask here, what is next? So until the 5G network has a very good capacity and can achieve a lot of can achieve higher KPIs. Now, from 5G to 6G, the evolution from these three use cases that are already exist in 5G. Also in 6G, we want to increase them, but they will not be considered as a shift in paradigm or transition in technology. The key enablement or the key factor to go from 5G to 6G really is AI, the implementation of AI. Why AI? We want AI to be ubiquitous. That means that it's available for every user and everywhere. And we want the network to be intelligent. For example, to achieve sustainability, the network should be intelligent enough to decide how to use efficiently the energy. The artificial intelligence can be used in telecommunication, for example, for optimization. We mean by optimization is that to select the appropriate set of parameters to enhance the performance of the network without changing or without spending money. This is what we mean by optimization. We can also use AI in predictive maintenance to predict when system can potentially fail or get some maintenance issue. We can use also AI for customer support, like those chatbots used by mobile operators, and we can use it also for security, like fraud detection. As a starter example, we have an implemented model called Timing from China Telecom, which is the largest telecom operator in the world, China Telecom. Here we have a scenario where we have our network of interest here, and we have the technical staff, the engineer. So the engineer wants to optimize this network. Before AI, the engineer should get information about networks, should read the status of the network, and decide which parameter to adjust, then implement this script. So everything is done by hand, let's say. Now, with using this AI, first the user or the technical staff, the engineer, will instruct or give a question to the AI. Let's optimize our network, etc. So the user will give a prompt. The AI will send a query to what we call a knowledge based. This entity will contain every specific details about network, architecture, configuration, and technical specification of our equipment. You can like the technical document with the architecture or design of our network. After that, after getting this information, this insight about our network, with the prompt of the user, with the prompt of the user, the LLM or the AI can understand uh, really the question or the request of our user. After that, it can send requests to the database to get relevant network statistics to the prompt of the user. Then, after getting network statistics, the AI has the power to inquiry business and operation and management stuff. So we can get information not only technical, but also from non-technical stuff. After that, we can inquiry the network to get real-time status of network and real-time data. After receiving all this information, so the AI can direct or can limit the response or the answer to the precise operation to be made. After getting all this information, we came to decision-making process. It can be automatically done by the AI or by intervention of the user. This is a simple example of implementing AI to implementing AI to adjust optimization or network parameters according to optimization question or prompt from the user. To implement AI in telecommunication, we have some set of interesting model. Since the mobile network contains a lot of temporal dependencies and sequential data, models that are capable of treating sequential data are interested. Are interesting for our problem. For example, we have LSTM, which is a recurrent type of recurrent network. And we have transformers and mixture of experts and multimodal architectures. We will see them one by one. The recurrent network are just a neural network with feedback. These networks or these AI models are specialized in treating sequential data. For example, here we have this sequence. The RNN or the LSTM will process every input one by one. So here this input is number 3, which is the first input to the network. We'll get here after some processing. Then the network will get we preserve some memory about this sample. Then it will process the second and the third one by one, and at every step it will adjust its memory inside internal memory. We can say the same thing for LSTM with some optimization to avoid some known problems in RNN. So for the recurrent network structure, data are sequential and the processing also is sequential. So the main problem for this, we cannot parallelize the processing. With the transformers, we have another paradigm to deal with sequential data. For example, if we have, let's say, an NLP task of predicting the next word or understanding the text, with these two examples, we can observe that the first sentence contain the word bloody, and second also contain the same word. But depending on the context of these words, the neighboring words, the meaning of the same word is different. For the first example, the bloody shirt, we mean that just the shirt has some blood on it. But in the second example, we have the bloody crime, which means that the crime is very violent. So in the transformer model, instead of processing each input sequence, for example, it will process this word after this, then this. In transformer model, it will have to determine some measure between every word in sequence, the, then bloody, and then shirt. Here also the bloody and shirt. Then it will measure similarity of or the dependency between this word in sequence. So it can measure the impact of the similarity between the and the. So it should get some bigger number than the other. Here also the similarity between bloody and bloody will get some bigger number. The same thing for shirt would give some bigger number here. Let's say zero. I'm not interested in the value, but I just want to illustrate that this table show somehow the similarity or the impact of each word on its neighboring word. So using this type of measurement, the transformer will have an internal representation, let's say hidden embedding, for the first example of bloody, which will be some sort of vector, and first the example also we have a sub-example. The internal representation of this same word will be totally different in the transformer. This is the power of the transformer. This is why it can understand the context, the neighboring word. So depending on the neighboring word, the transformer will generate an internal representation. Here's somehow detailed mechanism of determining the attention or the measurement of similarity between words in sequence. Let's say here we have this sequence. How are you doing? To determine the similarity measure between these words, transformer first will apply some linear transformation. We have 3 linear transformation. So from the same vector, let's say this vector, after transformation, we get 3 different vectors. We don't want to focus on how to determine this vector or the meaning of each one of them. We just want to say at the moment that using this mechanism, the transformer can determine the attention measurements, which is used as a measurement of interrelationship between the word at same sequence. At the end of this process, we want just our transformer to get a hidden representation or an internal understanding of each word depending on the neighboring word in sequence. The other example or the other model that can be used in telecommunication is a mixture of experts. In this technique, instead of using one large model, one bigger model that can answer everything, for example, the well-known ChatGPT is a large model that can answer the question about every domain we can ask about it. Instead of this, in mixture of experts, we prefer to divide the task into sub tasks, or divide let's say, instead of using one model, we will use several models. We will use several models, and every model will be specialized in a very precise task. Let's say that the first one will be specialized in code generation. The second one, let's say, it will be specialized in regulation, law, etc. And we have the main node, or the main network here is called gating network. The gating network will have two rows. First, depending on the input of the user, the gating network will select which submodel can generate output. After generating the output, the total output will be a weighted sum of the output of these small models. So the gating network will generate weight with the output of submodels, and will select which model will be responsible to generate output. Another important model, or AI technique, is diffusion model. In diffusion model, we take an input, then we will add gradually some noise to it, then we will increase the noise until we have a completely noisy input. This is in the forward. Then the network will learn to do the reverse process. So we will take very noisy input, then it will reduce successfully the noise until it will get the original input. This diffusion model is very, very useful in telecommunication, especially in wireless communication. So using this, we can reconstruct the image, we can reconstruct the signal from noise, and we can also use it for channel estimation, or estimate some hidden parameters of the wireless system. Multimodal is also a key and important technique that should be used in order to be able to implement AI in telecommunication. For example, here we have a model that use inputs as image and will produce some text at the output. And we know that for image, the suitable architecture is CNN, and for text, which is sequential, SCM is more suitable. Same thing here, but the type of the input data here is sound. The problem here, or the complexity of the model, arises when we have to deal with two different type of network, for example, LSTM and CNN. Hopefully, with the advent of transformer and vision transformer, we can use transformer for process image input and text and other data modalities. So with the transformers, also multimodal AI is very simple in comparing to use the different models from different natures. We have here a case study for multimodal AI in telecommunication. We want to predict cell traffics in a mobile network. A mobile network is subdivided into cells. Each cell has neighboring cell. Here we have the C cell, which has as neighbor A and B. And we have, for example, a D cell, which has just B as neighbor. The input for this network will be the traffic load, which is from different type of data. It can be SMS, call, or internet. Then from this data, the network will generate graph of relationship between each cells. Then the graph will be processed by a network, and the inputs data also will be processed by another network to get finally the predicted cell traffic. This is the case when this is a case when we have to deal with a multi-model AI to predict something useful for telecommunication, which is traffic by cell. Another important application of AI in telecommunication is intent-based network management. In the terminology of 5G and modern telecommunication, we have three different categories of application. We have applications that require larger data rates, MBB, and we have delay sensitive equation, URLC, and we have IoT or massive time communication, which require a lot of connections. Since 5G is based on fully virtualized network, we have to deal with something called slice. Slice, you can think of a slice just as a virtual machine that has some configuration. Let's say RAM, processors, network, and storage. So if you want a virtual machine that have 188 RAM and processor with 20 cores, let's say network of 10 gigabits per second, etc. So we have to configure this VM or this slice. We have to attribute some resources to our slice. So in this use case, we want our system or our AI system to detect the configuration files, to generate configuration file for the slice, depending on the intent. So the user has not to specify explicitly that this application is eMBB or ERC or anything else. The user should just give a sufficient description of its intent. So, for example, we can give a folder that contain files like Excel, which has tables. We can give also this folder. It contain also images and PDF, maybe videos, etc. And depending on this data, the AI system should be able to detect or decide which slice configuration to use, and should be also able to output a correct NestJSON, a correct format for implement directly in our network. For the implementation scenario in mobile or in telecommunication in general, we have all sorts of possible scenarios. So we can implement the AI in the cloud for some application. For other applications that require some low latency communication, we can implement the AI at the edge, which are just servers located near the end user. And we have also some applications that require AI to be implemented in the mobile device. And we can also we can use architectures that split AI processing between cloud and edge and mobile users. When implementing AI, the problem are depending on the implementation scenario. For network edge deployment, we bring computation closer to the user, reducing latency and optimized bandwidth. Edge cloud collaboration. Edge cloud cooperation allows a smaller LLM to be at the edge when we use edge cloud collaboration, because servers at the edge are less capable than servers on the cloud. The real-time context-aware AI at the edge improves the quality of service and the mobile device. So for the challenges of implementing such network, especially the challenges are mainly consist of let's say the computation resources. So when implementing network in the cloud, don't have problem of computation resources. In the edge, we have somehow computation resources some limitation. But on the device, we are very restrictive. We have problem of computation resources uh, along with energy efficiency problem. So at the end, for referencing or for to give some special reward to the source of this presentation, which is a white paper called Large Scale AI in Telecom, which is available on the internet. And thank you for your patience. And sorry if I took a lot of time.